Hello everybody, welcome to our extra video for lecture 1. Yesterday I think we ran out of time because we had this, we have the chat and people were participating a lot, which I really like, and they were making a lot of super interesting questions. But I was not aware of the amount of questions I would have in real time. I think it will be hard for me to answer like all questions at the same time they appear in the chat. I think the best thing that we can do is maybe what I will do is I will ask you that if I am explaining something and you have a question, so maybe you can take notes on your side, and I will try to make a pause, for example, maybe at the end of the session, maybe the last 10 minutes of the session, so we can make a pause and ask for questions. Then I can read the chat and I can like discuss with you about this. Also, let's understand that some questions could need like a very large answer, right? So in that sense, it will be probably impossible for me to answer everything on the time we have on the class, right? Because we only have 50 minutes and we have a lot of material to cover, right? So I will ask you also, if you can, that maybe after each lecture, if you had a question, please pose your questions on Piazza. And it doesn't matter if it's answered already. I mean, actually, if I answer the question, it will be nice and it is a good exercise for you. If you can just go right away to Piazza, pose your question, and post the answer yourself, right? So it is good for you to like start a discussion about that. So I think that will be good. Also, I think I will try to get rid of this waiting room. So I'm kind of following the recommendations from the department, but I think the waiting room is causing more problems because everybody, I mean, not everybody is like connecting at the same time, and we have just a lot of people that I need to admit. So I will try to see if I can like get rid of those things and just admit everybody, and that's it. I mean, try to be on time, right? I mean, if we are recording the session, and obviously you can see the video later, but if you just log in to the meeting, like in the last 20 minutes, you will have a lot of questions for sure. There could be things that we already explained, and maybe you're asking something that is already explained. So yeah, try to be on time, and I think this will be great. Okay, so we were talking about topics in computer graphics, and some of those topics I didn't have enough time to finish to explain it. So when I say topics in computer graphics, this also means like areas of research, and in some sense, it's also kind of like applications of computer graphics. Why is that? Because I mean, whenever you find a new application for computer graphics, sometimes that application is so interesting and it has so many problems that we want to solve that in the end can become an area of study or area of research, and new topics and new concept will arise, right? So before, for example, before before we had the technology of 3D printing, for example, I mean, 3D printing was not a concept or a topic or something related to computer graphics because it just didn't exist, right? But now that it exists, there's a huge area of research in terms of fabrication related to 3D printing, right? So for example, one of my projects, I will show you a little bit of that. One of my projects is related to 3D printing. It's kind of like a mix between VR drawing, interaction, because it's like human computer interaction, how a human is interacting with a computer to draw stuff in 3D, and it's also related with surface reconstruction, and then with 3D printing, right? So in the end, like many things can be mixed. So we were again talking about topics in computer graphics. So we already talked about 2D imaging, raster images, vector images, and here someone had a question, right? Someone was asking if the air, I don't remember exactly the wording of the question, but they were asking like if in the end everything is pixels or everything is converted into pixels, why I can't see the pixels, right? So I will open Illustrator to show you what this means. Okay, so here we have Illustrator. Illustrator is a software package that is its intention is to exactly create vector images, right? So the intention of Illustrator is not to create raster images, but create like vector images. So if I have something like this, for example, this is letter A, and I zoom in, right? It doesn't matter how much I zoom in. This curve is just beautiful, right? And I never see the pixels. Why? Because this area is defined by, again, by curves, by Bezier curves. So these things right here are the control points of Bezier curves. And these things are called handles, okay? So if I move this handle, for example, I can modify how the curve is behaving. So there's an algorithm that is defining this curve, okay, based on the position of its control point and the position of its handles, okay, and obviously the position of the controls and handles of the next curve. What I mean that in the end everything is pixels is that we are seeing this on a monitor, right? And the monitor only understands pixels. So it doesn't matter how is my geometry, how do I like create the geometry. At the very end of the pipeline, at the very end of the graphics pipeline, I will convert everything into pixels. And specifically in this area of vector images, the algorithm is defining, right, which part is colored by white and which part is colored in blue, right? And there's another algorithm called the rasterizer algorithm that is in the end deciding which pixels of my monitor are going to be colored blue and which pixels are going to be colored white. So the pixels are there. When I say I cannot see the pixels, right, is that, of course, in terms of the space on my monitor per se, the pixels are so tiny that I cannot see them, right? So, well, actually you can kind of see here, this is called anti-aliasing, but you can see that this line is not exactly a perfect curve. I don't know if you can notice this. You can see this tiny like stair effect. Though that is exactly the rasterizer algorithm that is getting the information from the curves, translating those curves into pixels, and show those pixels into the monitor. In the end, what happens with vector images is that the pixels that the rasterizing is creating are exactly the same size as the ones that I have on my monitor, right? So that's why I will never see the pixels, right? When we are talking about Photoshop, right, raster image, when I say I can see the pixels, right, is because if I zoom in, there's no more information to recreate the image, right? There's only one tiny point or one tiny square of color, and when I zoom in, that tiny square of color in the monitor space is covering a large portion of my monitor, right? So it's actually converted into several pixels, right? But in the end, it represents a single pixel, right? So that's why I can see the pixels. And of course, I told you yesterday that this will be way more clear when we study the pipeline, the entire graphics pipeline, right? And we will do that on basically on the next week, because the following topics is the rendering pipeline and vertex shader and fragment shader. So I think everything will be you will understand better. Okay. But again, I love these questions. It is obvious for me that you were really paying attention to the class. Great, perfect. So let's just go back to the presentation. So as we said, in terms of 3D surfaces, we also have something similar. Surfaces defined by curves, right? And surfaces defined by polygons. And we also have surfaces that are defined by voxels, right? It's volumes. And again, someone was asking, so what is, in the end, what is easier to render, or what is fastest to render? This construction here, for example, this is Minecraft, right? So Minecraft is a world that is basically created by voxels. Please imagine this as a lot of layers. So there is an upper layer that is our monitor. So the monitor only understands pixels. The entire pipeline at the very end, it needs to just show pixels, right? Before pixels, we usually have triangles, because GPUs, they usually only understand triangles, right? I mean, it's not exactly like that, but right, I'm kind of like simplifying the stuff. So they understand triangles. That's like a layer below the upper layer, that is the monitor, that only understands pixels. And below that is the way we create that geometry, or the way we manipulate that geometry. So for example, in this case, I might have information about this volume. I might have an array with millions of cubes, right? Millions of cubes that are representing, for example, a mountain in Minecraft. It's not exactly like that, but imagine like that. Imagine that I could have in my CPU a super large array with all the information of the millions of cubes that are representing a mountain in Minecraft. And for every cube, I can have information, for example, of the material of that cube, also the color of that cube, the texture of, or many stuff, right? The amount of energy you need to, like, you need to imprint into that cube, for example, to get rid of that cube, right? I mean, when we were using in Minecraft, right, you can destroy these little cubes or create new cubes. So that is information that is not yet into the GPU, right? We haven't sent that information to the GPU. We have, it's way below in the pipeline. You're like playing with that geometry, right? So when you are literally, when you want to actually render that information, you don't need, for example, in this case, you don't need the information for rendering this mountain or these shapes here. You don't need the information from the cubes that we are not seeing, right? We only need information from the faces of the cubes that are visible, right? So there should be an algorithm that needs to say, okay, I have all this volume information. I have millions of cubes that are representing this mountain, right? But I will only render the outer surface of this. So there's an algorithm that it needs to identify which cubes are actually visible, and from these cubes, which faces of those cubes are actually visible, and it needs to identify for each face on each of those cubes, you have two triangles. So there's an algorithm that in the end, it extracts that information, and it's defined the number of triangles that are only visible from that view in particular. And those triangles are the ones that you send to the GPU, and you basically render based on those triangles. And there's a certain area in the GPU, right, in the rasterizer of the GPU, that it will convert those vertices, sorry, those triangles into pixels, right? So that's why yesterday I was saying, in the end, everything will eventually turn into triangles, and eventually will turn into pixels. Yeah, but again, beautiful questions, and how much time it will take a render literally in rendering. It depends on a lot of factors. It depends on the amount of geometry you send to the GPU, the amount of information you're sending, the amount of lights or effects or whatever. Okay, so we were talking about voxels, hexahedral meshes, sorry, and tetrahedral meshes, procedural modeling. You already see this. Yeah, so in terms of rendering, for example, in terms of online rendering, I wanted to see you this demo. You have the web page there, but I can show you the demo right now also. So this is a very cool demo. This is using WebGL, and it shows a very nice scene in which you have several things. You have a very nice rendering, you have lightning, and you have several objects, but also it has like a very nice effects in terms of simulating the water. Okay, you can even grab the ball, and I think you can apply gravity, right? And you can play with that. So this render right now, this is real-time rendering. This is a rendering that is computed with WebGL, that is basically sending all the information to the GPU and is basically render everything in real time. So this is an example of online rendering. As I said, offline rendering is different. This can be computed on the CPU, also could be computed on the GPU, and it's just to create like super realistic images. We will discuss this like really in depth, because you will write your own ray tracer that is basically an offline rendering technique. Yeah, we said it's a couple of things of animation, simulation, we already said about that. This is another thing that I wanted to show you. Again, in simulation, there's also simulation in real time and simulation offline. Simulation that is created, computed, and rendered in real time using the GPU, and simulation that is usually way more complex. For example, this like simulation of huge waves to like smash a boat or something like that for a movie, right? That is definitely an offline simulation and takes way more hours for a computer to simulate that, or like super complex scenes, right? Let me show you this example. Okay, so in this example, this is also rendered in WebGL. You can also check the code actually. So there's a link to the code. I mean, it's OpenGL. Again, I will explain everything, but OpenGL or DirectX are the actual software or the actual framework that can, in the end, paint pixels on your screen, right? And there are certain technologies associated with those. So one of the technologies that is associated with OpenGL is WebGL, that is basically a graphics pipeline that works directly on your web browser. And 3.js, that is also a technology that you will use, is just a library that works on WebGL, and it just makes your life a little bit easier. Okay, so this is working on real time on my GPU and on my browser, right? So this demo is about simulation, and this cube right here, it will contain particles, right? So depending on the size of this cube is the amount of particles I will have. So you can see that moving this, it will create the certain number of particles. The way it will create particles is literally by voxelizing this cube, right? So voxelizing is taking a volume and discretizing a volume into tiny cubes, right? It's like, we can also, again, I said that in case of an image, it's a space that is discretized in tiny elements, which are pixels, right? And the very interesting part of this is that you can also, so you can play with this area. You can also create like new cubes or new areas with more particles. And again, each of these volumes will have a certain amount of particles, because it will get voxelized. So when you press start, all those voxels, all those particles start to interact with each other. Yeah, I don't know about you, but I can see this for hours. No, I'm joking. Not for hours, but it is really nice. I mean, it's not super realistic, It's but it's a good approximation. It's a really good exercise and not super realistic. It doesn't have any viscosity controls or anything like that, but it's really nice. And it's a good example of what you can achieve in real time and in browser, right? I mean, this is crazy. And as you can see, for example, if I click on the particles, I am like imprinting force on the particles also. So they are reacting to the movement of my mouse. Yeah. We already talked about digital characters, and here's where I stopped yesterday. So I wanted to talk about virtual reality. This is one of my projects, and it's basically we were studying how people can describe surfaces in 3D using a VR drawing tool, and we were reconstructing a surface from those drawings and to be able to like 3D printing. So I will show you the video. And that's my wife and my kids, by the way. That was my daughter. Um, so yeah, so basically you can draw something in VR, and those sketches can transform into a mesh that can be 3D printed. So in this case, it's like we're telling the story of a mother, right? That she's not a computer scientist, and she can just have fun and create a toy for her daughter, right? This is another topic, augmented reality. This is also super nice. It's similar to virtual reality, but in this case, you're augmented the reality. People is seeing the reality, and at the same time, you're like imposing a 3D image that is basically fitting the same view that the user is seeing. This is an example of a project I did. I don't know. I think this was on 2015, I think, or 14. I really don't remember. This was a very nice experiment. I will tell you a little bit about this. So what you're seeing here, it's a fossil. This is a molar of a Gomphotherius. So a Gomphotherius it was an animal that lived like 30,000 years ago. They were similar to a mammoth. Yes, I hope that is the correct pronunciation. So basically, this is a tooth of this animal. So this is a real fossil that has, between 30 and 35,000 years. So there's in my hometown, my hometown is Guadalajara, Mexico. There's this paleontological museum. I studied there because I'm a mix of several things. At some point of my life, I also studied paleontology, and so they contact us, and they contact us, and also they were like working with an elementary school in my home city, and they wanted to do something with the kids, right? And at that time, I was working on my university in Mexico in a media lab, in UP Media Lab. And this was a very nice project in which we did the experiment of bringing the kids to our lab. So in our lab, we were doing projects of virtual reality, augmented reality, and computer graphics in general. I mean, projects of computer graphics. And so we show the kids all the projects that we did in the past, and we explain them how they work, right? These were kids, they were I think in 4th and 5th grade of elementary. And then we will ask them if they could come up with ideas for a new project that could be related with the museum, right? Because in the end, the museum wanted to do something but something that could be appealing to kids of their age. So it's like, okay, why not? Let's just go and ask the kids, right? So it was very nice because what happened is that the kids, once they once they saw what we could do, right, and how this kind of works, yeah, they just came up with ideas. So they come up with the idea of, okay, it is possible to recreate these fossils into a like virtual environment, and if we could see the fossil as if it was in my hand. And yeah, we might, right? I mean, we didn't even have a scanner, so we had to buy a 3D scanner. So let me show you. I don't remember if this has sound or not. I think it doesn't have sound. So we have a 3D scanner, so we scan the fossils, right? And we had to reconstruct the fossils with all like the material and make a very realistic version of the fossils. And we had some markers, and we recreated using augmented reality. So the thing is, these fossils are very delicate, right? So usually the kids seeing the fossils inside inside a case, right? So they're very far from the fossil. So if they want to see the fossil from very close, it's impossible. They cannot manipulate that. It's kind of dangerous. But with augmented reality, they can, right? So yeah, it was just a very nice experiment, and it was nice because also in the end, the kids were not coding anything, right? They didn't have the knowledge to literally do the work by themselves, but we had the kids there in the lab, so they were going every other day, and they were literally asking. They were like our clients. They were, oh, put this thing here, or I don't like this part, or can we make this bigger? Can we make this other way, or whatever? So it was very nice because in the end we were like working for them, and I think there was a group of kids that they presented this project into in a international conference of education and things like that. So it was very nice. And so yeah, augmented reality is a huge area in computer graphics, and you can do a lot of things. And again, it's a mix of a lot of things, because in this case, it's not just the part of augmented reality is like tracking markers and render something in 3D that matches the reality. But a lot of things are involved here. I mean, rendering, because you need to render these fossils like in a very realistic way, right? So we had to do light baking and some tricks that I will show you when we will talk about that. So this is, for example, this is a mix of ray trace offline rendering mixed with real-time rendering, and it's very, very interesting. I will show you more details when we will talk about rendering. Capture is basically getting information either from objects or from the world into the computer, right? That is translated in this case into geometry, for example, and you can do things with that. So, for example, lidar scanning is it's a device that is like sending a laser that is moving and rotating and hitting in millions of points in your environment. So every point here, it's a place in which the laser hit, for example, the ground or the car or whatever. And the information that it can give you is the distance of that point, the distance of the point it hit, and also the orientation of the surface that hit. And you can do a lot of things with this. For example, there are companies that, well, self-driving cars, for example, sometimes they use this. They use lidar scanning to get a geometric reference, right, for their cars, and they can like use this with combined with machine learning algorithms and blah 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 to make the cars moving by itself. The sketching, this is also an interesting area. Let me see if it can sound. This is also a project in which I was involved. This is totally different. This project is the intention of this project is basically taking messy drawings from people, right, and basically clean those drawings. It sounds simple, but it's super hard. It's a very hard problem. So basically, from this messy drawing that you see here. That is, I mean, if someone is not as skillful in terms of drawing, they might draw something like repeating lines and things like that. So getting that information and deciding which groups of lines are in reality, or in reality they only represent a single feature, and make like the clean version of that drawing is really challenging. And this project is about this. And sketch is a huge topic already in computer graphics. There are a lot of things involved in here. As I said, part of my research is sketching, but in VR, in 3D. This is sketching in 2D. And there's also research that tries to get sketches, for example, from for objects, industrial design objects, and recreate the surface or recreate the object in 3D only from a 2D image. And these are applications for computer graphics. Again, it can be similar to the topics, because a topic can become an application, or an application can become an area of research or whatever. But it's just like expanding a little bit of what we talk. So movies, games, computer, industrial design, machine learning training. This is a very interesting, actually, by the way, machine learning training. So very recently, this driving cars, right? I mean, many companies right now are working on that, on driving cars. The way they were training the driving cars before, it was just by taking the cars into the real world, right? Like taking the cars to drive in certain areas so they can like test the cars. But now they can do that virtually. So this is an example. For example, this is a company called Aniverse. It's from a very good friend of mine. His name is Victor Gonzalez. He's from Spain. So his company is basically, they have, I will talk a little bit more about him. He has a company called Next Limit, and they created one of the most accurate render engines that there are in the industry, right? So they're very good in creating synthetic images that are super realistic. So he created this new company, Aniverse, that is basically creating synthetic images that are super realistic, but they have the intention of training self-driving cars. So now you can have the algorithms for the neural networks for training the cars, and instead of having to take the car outside, you can train the car using synthetic data, and you can simulate whatever condition you want, whatever conditions with like fog conditions or lighting, different circumstances, people cycling or whatever. This is huge, and it is, again, it's computer graphics. Computer graphics, in this case, applied to train self-driving cars, for example. So again, there are a lot of things involving computer graphics, and I wanted this intro to be like a very inspiring moment for you, right? Because this could be the first step for you into computer graphics, right? I mean, maybe some of you could eventually do a master's degree or a PhD, or work in a company that is related with animation or fabrication or whatever, and this is a world that is really nice. There's a lot of money in this area also, because computer graphics, one of the biggest applications of computer graphics is obviously video games and movies, right? And there's a lot of money in there. People, they want all the time, they want I mean, we want movies or TV series or whatever all the time. We want new things, and all those new things we want with more effects and explosions, and everything needs to be more real or whatever. So there's a lot of money invest, right? And because those companies and those industries have a lot of money, they also invest a lot in research, right? So it's a very nice area, and it touches many things. So if eventually you have a question of, is this could be computer graphics, or if you were still wondering how much you could do with computer graphics in general, you should see SIGGRAPH. So SIGGRAPH is the most important conference from in the world related to computer graphics. They have a journal called Transactions on Graphics. This is part of the ACM. SIGGRAPH means a special interest group in computer graphics. So SIGGRAPH is a huge conference, and every year they have two conferences, SIGGRAPH and SIGGRAPH Asia, and they accept the best papers of the world, and it's just amazing. And this is the preview from the SIGGRAPH from 2020.
Present clips from just a few of the exciting breakthroughs in the technical papers program. A learning-based approach to keyframe video stylization enables this artist to craft a personal look in real time. By using 4 fisheye monochrome cameras, we can track someone's hands in space, enabling them to sort
This
through
is
blocks
interaction,
and win the game. Using clever hinge design, a flat lattice of thin, flexible strips can be deformed into a complex 3D structure and then flattened back out again. To create a realistic knit bunny, this algorithm uses an energy density function to drive a thin shell simulator. It can also knit armadillos. By interpolating a sparse series of 3D poses, this algorithm produces smooth, complex motion that still allows for artistic control. This algorithm supports immersed bubbles and free surface flow simulators, producing
way
the
more
familiar
examples.
glugging
You can
action
go
of
and
water-cooled.
just go to YouTube, and you go and you look for SIGGRAPH technical papers. You will see all those videos. You'll see like the preview that they made every year for SIGGRAPH and SIGGRAPH Asia, and also most authors they also upload to YouTube. They upload videos of their projects, so you can also see a lot of projects. And if you are really interested in like reading papers about this, if you have access to a lab in UBC, I mean, if you are working in a lab in UBC, UBC has access to the ACM Digital Library. But if you don't have access to the digital library, or you're in a different country or whatever, this webpage here, kesson.realtimerendering.com, this is Professor Kesson Huang, and Professor Huang, he's basically compiling all papers from SIGGRAPH and SIGGRAPH Asia and Aerographics, that is basically the European version of SIGGRAPH. And yeah, you basically can read everything from here, and it's perfectly legal. This is not any problem. It turns out the thing is, ACM and SIGGRAPH allows the authors to publish their work in their own webpage. So what this professor is just doing is just go and he needs to find all the personal webpage of all those authors, and he grabs the links for everything. He's doing an amazing job. So for every year, you can go here, for example, 2020, and you can see all the papers here. And for every paper, it says obviously the name of the paper, the authors. It says if it's like the document, the video. Sometimes they have code, and yeah, there's a lot of information here. So it's endless, and it's super interesting. Great. So this we already covered yesterday. What you will learn, we already said that yesterday. We already said this yesterday. I also said this, required software. Yes, again, required software. This is the software that we will use on the assignments and class and everything. This is what you are required to either learn or practice or do on your assignments. Supporting software is software that I will use. You also could use to support the learning. Usually is the software I use to explain stuff. You don't need to know this. You don't need to use it or have this installed in your computer. And we already said about this. We already talked about this. So again, these are the communication. Everything goes on our website. We are modifying the website every time we need. And these are the books that we are using right now. All these books, you have access to the books from UBC. None of the book is, I mean, it's not mandatory to have or like buy or something like that. But we will recommend like, oh, it will be better if you read this part, or you can read this part, or whatever, right? So yeah, you have access to those books, and we will recommend to read these books. And we might add other books. I already have at least a couple of books already that I might have, I might add to the list. Uh, Again, the grading, I spent like 3 minutes yesterday explaining this, and this is super important, and I would like to explain a little bit more. So first, at the bottom says 3 late days for use during the term. So again, for all your assignments, you have 3 possible late days for using. Okay, you can use those 3 days on the first assignment or on the last, or you can decide to use them in different assignments, right? That is up to you. You have an extra late day for intro because this problem we have of starting late. So only for that one. So that extra is not that you have 4, right? You have 3 for everything, and only for the intro you have 1 extra late day. And again, how those extra lates work? They count weekdays. Okay, so usually I will put the deadlines for assignments on Friday. That means that if you, instead of delivering your assignment on Friday, you deliver on Monday, we are not counting Saturday and Sunday. We will only count as a late day. We only count Friday. Okay, that's it. If someone eventually run out of late dates, I mean, it usually doesn't happen, but if someone for some reason you don't have late days anymore and you have problems to deliver something, please send me an email, and eventually we can, I mean, if we need to wait for you to deliver something and you already ran out of late days, don't expect to have full marks. So we will probably get rid of a lot of marks, but we will need to negotiate, right? So I am open to negotiation, but that negotiation will be hard, and you need to ask in a personal email, ask me directly. But this usually never happens because 3 late days is a lot, again, because you're including all the Saturdays and Sundays that you might use. Okay, and bonus points. Again, this is super important. So transformations, shading, ray tracing, and theory, they all have bonus points: 4, 4, 8, and 4 points. When you will see the descriptions of those assignments, you will see that we have a certain features that we ask on the assignment, right? And all the assignments will be over 100 points. And there will be optional features that we encouraged you to try, right? Those optional features will be hard stuff. So this basically is like taking the course in challenge mode, right? So for every video game, you can play a video game in like easy mode or challenge mode. So this is basically taking the course in challenge mode. And if you get those features, you get those bonus points, and those bonus points, the ones for those 4 assignments, those bonus points are directly going to your final exam. So if someone, right, can get all the points, all the bonus points from all those assignments, it means that the day of the exam, she or he has 20 points already. From the 100 points of the exam, you have 20 points already, right? So starting an exam with 20 points already will be really nice. So yeah, so try it. Try to get the bonus points, and it will be great, right? Because in the end, those challenging futures, you will learn a lot of those, and you will get a lot of practice on like more complicated, more complex things, and believe me, you will be very proud of yourself of getting those futures. Also, midterm 1 and midterm 2, there's something there. It calls 2-stage exam, and it says TBD. So let me explain something. Usually, the way we do the midterms and the final exams, at least in computer graphics, and at least on all the courses that I've been involved in in UBC, right, is that it's on paper, right? So you come to the class and you have 1 hour and you have a paper and you basically need to write your midterm or final exam. So basically it's synchronous, right? Everybody needs to be there. As I understand, there are some professors are performing right now, I mean during the pandemic, they are performing the exams also synchronously, right? So it's you set a date for the exam and everybody needs to be there, and there's this invigilation process in which you need to turn your camera on and people needs to see you at the same time you're performing the exam, all those things. I believe that that is not ideal for someone that is on the other part of the world, and basically is not in the same time zone. So I think it could be not fair, right? And again, this is my personal opinion. I'm not criticizing other professors, so please, I'm talking about my course exclusively. I don't want to ask my students to be on time for an exam, and that some of those students are taking the exam at whatever 3 p.m. and for some other students that time is their 3 a.m., right? That will be, it will be harder for them, right? I don't know if I don't know if you are working or if you are taking other classes or if you have other responsibilities, personal family responsibilities. I have no idea, right? So yeah, so my idea right now is that the exams will not be synchronous, so they will be basically open book exams. So we will deliver the exam and you can solve it, right, individually at your home using whatever material you want. You need to cite every single material you cite, and every single material you use, and that's it. So we have a deadline, you deliver your exam, and that's it. This thing of two-stage exam is a very interesting type of exam that is sometimes used in UBC. I don't know if you already know this type of exam, two-stage exam, but basically this is that we have 80, in this case it will be 85% of the exam is in stage 1, 15% of the exam is in stage 2. So stage 1 is individual. So we will give you an exam, you solve the exam individually, right? Open book, but you solve it individually, and that is 85% of the exam. And then you deliver that, and then we will give you another exam that is in the end very similar to the first one, but you solve that exam, the second stage, you solve that in teams, okay? So you get with 3 or 4 people, we will decide that later, between 3 or 4 people, and you need to discuss the exam, and you basically need to solve the exam between everybody. That is very interesting in terms of learning, because you can immediately understand, oh yeah, maybe I made this mistake in my individual part, right? You can understand why you forget to do something or whatever. You can explain others something that maybe you actually did understand very good, and it's a very good team effort, right? So you will collect 15 points from your exam on this second stage that is basically like a team, right? So we will do that. I haven't decided if I will do the same 2-stage exercise for the final exam. Depending on the results of midterm 1 and midterm 2, I will decide how we will proceed for the final exam. Yeah, so that's it. That is in terms of exams and this 2-stage and whatever. Again, participation, I will post quizzes on lecture days. Not for every lecture. For example, for the first lecture, I didn't post anything. So for most lectures, I will post a quiz on Canvas with a couple of questions, and you need to go there and answer those questions, and we will take that as participation. If someone, for some reason, eventually don't have that participation, but is incredibly active in Piazza, and please hear my voice, incredibly active in Piazza, that could count, not maybe, that could count as participation, right? But please the participation is those quizzes that I'll put. That for me is a way of checking if people is actually seeing the videos I'm doing, right? So I'm putting a lot of effort in give you content. For example, right now, I'm already took 50 minutes in extra time for lecture one. So obviously, if I create content, I want my students to see that content, right? That is the ideal. So participation in the end, it will tell me if you are actually seeing this thing. Sometimes sometimes at UBC participation is mandatory, right? And if you don't have that participation, you basically fail the entire course. I don't want to get into that extreme, but please, I will encourage you. You need to answer those quizzes, okay? And someone was asking if you could get if you solve the assignments with someone else. No, unless we say that on the description of the assignment, is not permitted. Okay, so yeah, I mean there are a lot of things that you could do, but yeah, unless is stated, is not permitted. So no, the assignments are individual. If eventually we consider that some assignments could be done in teams, that actually some of those will be done in teams, we will tell you, right? Yeah, and finally, something super important. So again, assignments are individual, and you can obviously use like internet to help you to solve the assignments, of course, right? And it means that if you're working in with for example, the first assignment, you need 3.js and you need WebGL, and you need to write some shaders, vector shader, fragment shaders, and whatever. And yeah, you might found a web page in which from which you just copy paste a certain part of the code or whatever. If you use any external source for your assignments, you need to cite that source. If you don't cite it, that will be a huge problem. Okay? If you cite it, is not a problem. Okay? And the thing is, we understand that sometimes we learn by example. So for some people, it's easier to have the problem, an open problem, and just come up with a solution, because some of you have more experience. Some of you, I'm pretty sure that some of you have absolutely no experience on JavaScript, and some of you have maybe 3 years of experience in JavaScript, right? So of course, everybody has different background, right? And I understand that. So for some of you, it will be maybe super easy to just come up with a solution. For some of you, maybe you prefer to just go find a code and see what this code does, right? And basically learn by example and use that on your assignment. So again, if you do that, you need to put that on your code. So you put comments, right? For this part, I use examples from this web page. I copy paste this part of the code, blah 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 blah. And the thing is, we will check if you use if you use resources from other part, we will check if you really understand that part. So what is, again, so using content or get inspired from extra content for your assignments, it is allowed if you cite the material. And but what is not acceptable is, I will make a, maybe it's a dumb example, right? But imagine that someone literally finds the exact solution. I mean, that will not happen, right? I mean, the exact solution is not, it can be exactly outside, because we are creating these templates, right? From scratch. Not from scratch, but yeah. But imagine, right, for a moment, that someone somehow finds the entire code of the assignment, right? And it just literally just copy pasting, right? So it copy paste and it says, okay, I copied the entire stuff from this thing, right? But he or she cannot explain anything from that code. That is absolutely unacceptable, right? So if you are going to use something from other side, it's acceptable if in the end you learn from it, right? If you can, because we will do peer grading, right? So remember that. So if if at the pre-grading review you are citing something and you're using 2 lines of code from someone else, but you have no idea of those what are those 2 lines of code are doing, then you will fail. Okay, because in the end is, yeah, you just copy paste something and you are not learning anything. So it would be very different to say it was super hard, I was literally stuck, I couldn't find the solution, I just went to internet, I found this, and I saw that it was working, and I just dive in the code and I finally understood, and this is what I got, right? So in my previous experience, actually, what I usually expect from someone that uses code from other part is that maybe they use that code, right, to maybe to finish the first features from the assignment, and they use that for literally understand and learn everything about the assignment, and then individually they, for example, they tried bonus point and they collect some bonus point, and they can say, I was stuck, I got this example, I learned by example, I copy paste this, but I really learned, I could understand this part of the assignment, and then I had the courage and the knowledge, enough knowledge to try this bonus point, and I could make this new feature, and I did this by myself, right? Because I learned from this part. That is the ideal. I will applaud that, right? That is perfect. Okay, great. And so yesterday I said the expected outcome is to have a lot of fun learning this, and the assignments, especially if you can collect the features that will be for extra points or bonus points, and specifically the ray tracing, if they're very good, we could send these things to the SIGGRAPH faculty submitted student work. So basically this is that, again, SIGGRAPH, remember, is the most important conference in computer graphics. So having your name on SIGGRAPH is super important. I mean, you will not be able to create a paper, a technical paper on this course. If someone can, it will be very nice. But yeah, I mean, that is obviously not what we expect. But you can produce something that is very nice in terms of student work, and we can send it to SIGGRAPH. So SIGGRAPH has a special area in which they show work from students, and it's very nice to have your name there, and it's very good in terms of your curriculum, right? So I think the submission is on June or something like that. So we will not literally submit your work on this term, but I would like to have enough quality on your assignments at the very end, to send something to the SIGGRAPH faculty submitted student work, and we will help you to get into that level, right? Good. Next lecture will be the math review. I will try to record the math review today. If I can't finish today, I will do it tomorrow. For now, please check Piazza, check the intro assignment, check a couple of WebGL tutorials, play with 3.js, and also, I mean, again, I will probably post the math review today or tomorrow. We have class on Monday, but you don't need the math review for the class on Monday. So don't worry if you don't have time for check the video today or tomorrow. And yeah,